1955, a Lockheed P-2V Neptune, equipped with a revolutionary new means of aerial navigation, prepared for flight from San Diego, California, to the Naval Air Station at Key West, Florida. Eager to try out this new navigational equipment, the aircraft's navigator cranked in the coordinates of the point of departure and the desired ground track. He then pushed the start button and sat back to observe. Throughout the flight, the equipment automatically and continuously displayed ground speed, drift angle, ground track, also ground miles, aircraft latitude, and aircraft longitude. The navigational information for this flight was provided accurately without the aid of ground facilities, without regard to weather conditions, without celestial references, without reference to airspeed, and without knowledge of the speed or direction of the wind. In this flight from San Diego to Key West, Florida, the aircraft arrived at its destination with a navigational error of less than 1% of the total distance traveled. Accurate navigation is required for flights anywhere over the entire surface of the Earth. In conditions of poor visibility, in high winds, in turbulent flying conditions, over calm seas and over the roughest sea, over every type of land, including the polar regions. The navigational equipment must have no practical low-altitude limit and no practical high-altitude limit. It must be adaptable to all speeds, from the zero and negative speeds of helicopters and vertical takeoff and landing aircraft to the supersonic speeds of the most modern high-performance aircraft. Now, consider the shortcomings of navigational techniques utilized during the past centuries. Celestial navigation requires good visibility and takes time-consuming intricate navigational computations. Manual dead reckoning is inaccurate and requires the constant, undivided attention of the navigator. Automatic dead reckoning navigation on the basis of estimated wind and true airspeed data removes some, but not all, of the manual computations and time lags. Furthermore, errors in the airspeed data and the wind estimates cause the automatic dead reckoning systems to exhibit large errors. The use of radio navigation demands an extensive network of ground stations. During time of war or emergency, these radio stations undoubtedly would be silenced in both friendly and enemy territories. Navigation by means of radar mapping is obviously impracticable over most of the Earth's surface. The answer to modern navigational requirements is the use of continuous wave Doppler techniques. This principle utilizes measurement of the frequency shift of microwave energy generated by the airborne Doppler equipment. To provide a connection to the ground, the microwave energy originated by the CW Doppler set is concentrated into narrow beams of radiation. A portion of the energy is transmitted along each beam at frequency Ft. Energy is reflected back into the antenna at frequency Fr. The reflection of energy results from the dispersion of the incident energy caused by the roughness of the Earth's surface. With beams directed aft, the frequency Fr of the reflected energy is lower than the frequency of transmission because of the component of the aircraft's speed away from the ground along the direction of the beam. The difference in frequency is proportional to the component of the aircraft's speed along the beam axis. The higher the aircraft's speed, the larger the frequency difference. This frequency shift phenomenon, known generally as the Doppler effect, is the basic principle used in Doppler ground velocity sets to measure the speed of an aircraft in flight. With one microwave beam, only one component of the aircraft's speed can be measured. However, With two beams of radiation and barometric altitude data, it is possible to compute the aircraft's heading speed, VH, drift velocity, VD, ground speed, VG, and drift angle, delta. Additional beams can be added to meet the special requirements of helicopters and airships. It is the application that determines the number of beams required. The ground velocity data obtained with the Doppler set is the basic output from which other vital navigational data is generated. It can be directly integrated to provide ground miles, or it may be used in a navigational computer along with true heading information for the determination of the north-south and east-west components of the aircraft's velocity. Then, if desired, the north-south and east-west speed data can be automatically integrated to obtain the north-south and east-west distances traveled, which, in turn, can be converted to the latitude and longitude coordinates of the aircraft's present position. Knowing the present position and the desired destination, the best course and shortest distance to that destination can be automatically computed and displayed. To meet the requirements of certain applications, the ground speed, VG, may be combined with true airspeed, TAS, for automatic determination of the wind speed, VW, and the wind heading, HW. Accordingly, Doppler navigational sets, which provide navigation without reference to wind data, actually permit the automatic computation and display of the wind speed and wind direction. Continuous wave energy for the navigation set is generated by a tiny, extremely rugged, and highly stable klystron oscillator. The frequency of its output is in the interference-free band centered at 13,300 megacycles. The klystron, which is usually located between two microwave crystal mixers, not only serves as a rugged microwave transmitter, but it also acts as a local oscillator, coupling small portions of its power into each crystal mixer. The crystal mixers combine the small portions of reference energy from the klystron with the ground return energy and produce two signals, or Doppler frequencies, proportional to the components of the aircraft velocity along the directions of the two beams of the antenna system. The simplicity of the CW concept eliminates the need for IF amplifiers, local oscillators, or automatic frequency control circuits. The klystron and the crystal mixers are mounted on a featherweight but rugged antenna of very unique concept and design. This antenna unit features virtually 100% reliability, and there are no adjustments or moving parts. Further, it requires virtually no maintenance. The microwave plumbing is sealed in place within a septum, which separates the transmitting and receiving halves of the antenna. Note the twin feeds used to provide the two microwave beams associated with each reflecting surface. There are two feeds for transmission and two for reception. The antenna is sealed by integral radome sections. One section serves as a window for the outgoing energy, and the other section serves as a window for the ground return. The antenna has an integral shroud rigidly connecting its reflecting surfaces with the radome sections. This shroud is trimmed to match the contour of the aircraft. All Ryan antenna systems feature simplicity, high reliability, and adaptability to the space available in various types of aircraft. In particular, note how the antenna shroud permits rigid flush mounting. No aerodynamic drag is introduced. Another characteristic of Ryan CW Doppler sets is the orderly arrangement of parts within functionally organized plug-in subassemblies. These subassemblies feature advanced etched circuitry and pictorial identification of parts. Etched circuitry is also used for the interconnection of subassemblies. Troublesome interconnecting cables are minimized. This unit typifies the orderliness of the design concepts used by Ryan. The equipments are designed for rapid maintenance. Much design effort has been expended to minimize the training requirement and to achieve ease of operation. The visual outputs are ground speed and drift angle, displayed on a 3-inch cockpit instrument with integral illumination. A point of special significance is that Ryan navigation sets may be interconnected with other equipment to provide more comprehensive systems suited to an almost unlimited variety of specific missions. Regarding usage, it is important to note that the combination of Ryan navigational equipment and other computing systems provide the signals required for accurate stabilization of search radar against the motion of the search aircraft, and for accurate control of the stylus of a plotting board. Ryan equipment is also associated with development in the digital computing field. For example, it has been combined with digital computers to form a vital part of bomb director sets used in certain versions of the Douglas A-3D Sky Warrior. Now let us see the role played by the Ryan navigational installations in fighters and smaller attack aircraft to provide a featherweight navigational system which is especially applicable to the Douglas A-4D Skyhawk and other attack or fighter-type aircraft. Adaptability to available space in very small, high-speed aircraft is demonstrated by this A-4D installation. For example, the maximum antenna aperture width available is 7 inches. This unique installation was accomplished by employing separate, long, narrow antenna assemblies. The port beam is transmitted through the aft radome, and port beam echo energy received through the forward radome. A like assembly is employed for the starboard beam. These Ryan navigation units provide the same performance as antennas of single-unit construction with equivalent aperture area. Simplified cockpit instrumentation continuously provides visual navigational information which guides the pilot accurately and reliably throughout the flight. Large navigation errors due to errors in estimated wind speed and direction are completely eliminated. The Ryan Electronics Division has developed an integrated self-contained navigational and flight instrumentation system for Army aircraft. This all-weather set utilizes continuous wave Doppler sensing techniques. It will play a major role in the Army's nap of the Earth concept and the other advanced tactics characterizing our modern Army. It is a complete, integrated navigational system comprising a Doppler set, navigational computers, navigational and flight control displays, a vertical reference, and a heading reference. The basic system is designed for fixed-wing aircraft applications. However, low-speed accessories may be added as required to provide for the very low speed and the hovering requirements of helicopters. For rotary wing aircraft, this hovering indicator is provided to display heading speed, drift speed, and vertical speed. It provides the Army increased flexibility in combat areas, and it eliminates the need for ground radio stations with their attendant cost and vulnerability to attack. Flight tests have demonstrated an accuracy capability of 1 to 2% of the distance traveled. This is another Doppler navigational set designed for use in Navy helicopters. It utilizes 4 radar beams, weighs approximately 30 pounds, and operates from 0 speed to plus or minus 150 knots. This system automatically and continuously displays the heading speed, the drift speed, and the vertical speed of the helicopter. Outputs are provided for tie-in with automatic stabilization equipment to permit smooth and safe automatic transition from cruise speeds to a hovering condition. It permits sustained automatic hovering under conditions of poor visibility with better precision, operating under the best of weather conditions. This navigation set is a vital link in the Navy's all-weather ASW helicopter instrumentation program. It is in production. You will find these precision-built equipments operating in the study of jet streams, in the setting of speed records, in the recording of the Earth's magnetic field, in new missions over the ends of the Earth, vertical envelopment operations. In hovering operations to catch the lurking enemy below. During extensive anti-submarine operations. In aircraft screening the far perimeters against aggressive danger. In directing aircraft back to base. In low-level tactics. And in vehicles blasting off into the unknown. Guided by the eyes of flight.